I thought what I would do is go back and visit some problems from a pre-calculus honors textbook, because these problems are going to help you set up the problems in section 4.4. And the setup is the hardest part, so I felt it was worth a day. It was worth a day just to practice the setup. And the goal in section 4.4 is to find maximums and minimum values of things. But to find the maximum and minimum value of things, you have to find the derivative. To find the derivative, you need to have a function. So what you're going to have to do in section 4.4 is write your own function. That's what this lesson is going to help you do. So in example 1, we've got a rectangle inscribed in a semicircle of radius 2. So if you don't mind, I'd like to just sort of pause for a second and introduce, if you haven't been introduced already, to this equation of a semicircle. Anytime you have y equal to the square root of a number squared minus x squared, that's the equation of a semicircle of radius r. And the center of that circle would be 0, 0. So anytime you have an equation with that looks like that, the graph would have a point at the center, or sorry, the center would be at 0, 0, and then you'd go up r, right r, and left r, whatever r is. And you would have a semicircle. So in this scenario, the semicircle had a radius of 2 because it was 4 inside the square root. So to get your semicircle, you go right 2, left 2, up 2. So that point right there, even though it's not written, is at 0, 2. Okay, so inside that circle we have a rectangle inscribed. And the first thing we're being asked to do is express the area of that rectangle as a function of x. X meaning the x-coordinate from this point P where the vertex of the rectangle intersects the circle. So the rectangle and the circle share that same point. So what you would have to consider is what the formula for area of a rectangle is. And there's two different ones. Some people think of it as length times width. Some think of it as base times height. But really all you're doing is multiplying the two dimensions together. So I need to somehow get the base and the height both in terms of x. And therein lies the challenge. So we come to the graph, and I notice that if this point goes out a distance of x, so this point goes out a distance of x, that would make the distance from the center to the edge of the rectangle, that would give that a distance of x. So then, since the rectangle is symmetric over the y-axis, like this side is equal to that side, then that would make that length on the left also equal to x, because you have to go over x to be able to get to that x value. Then the height of this rectangle, so this height right here, is equal to y, the y coordinate of this point, because to get to this point P, you'd have to go over a distance of x and then up a distance of y. Well, we need to get them both in terms of x. I have this one in terms of x, but I need to get that one in terms of x. So that's where the equation that was given to you earlier comes in handy, because this equation tells you how to find the y values. So I just set y equal to that equation, because that's how you get this y value. The way you would get that y value of that point is you'd plug that x value, whatever it is, into this equation. You would do 4 minus that value squared, take the square root of that, and that would give you your y value. So this is what y equals in terms of x. So then, if you want to get the area as a function of x, you would just take the length of the base, which ended up being 2 of those x values, times the length of the height, which ended up being that expression right there, square root of 4 minus x squared. And that is the equation for area as a function of x. So in other words, if you wanted to figure out the area of this rectangle, you could figure out this length x, plug that value into this equation, and that would give you the area of the rectangle. Similarly, we're going to express the perimeter of the rectangle also as a function of x. So we need to recall what perimeter means. Perimeter is basically when you add up all the sides. So I can see that I'd have 2 of these sides and then 2 of these sides. So you have 2 of the 2 x's, because the length of that side is 2x, and then there's 2 of them, this one here and the one on top. And then you'd have 2 of these heights, 2 of the y's, which we've already talked about is equal to the square root of 4 minus x squared. So you have 2 of those. So basically the perimeter as a function of x would just simply be 4x plus 2 times the square root of 4 minus x squared. So if you wanted to find the perimeter of this rectangle, you could figure out just that length x, plug that in here, compute that, and then you would have the perimeter of this rectangle, which is the distance around the outside. In example 2, we have a circle of radius r inscribed inside a square. So when a picture is not given to you, it's best to draw your own. Now remember, inscribed means that the edge of the circle is going to touch, like kind of be tangent to the side of the square, because the circle has to remain inside. And it's a circle of radius r. So we'll just call that r. And what we're going to try to do in part A is express the area of this square as a function of the radius r of the circle. So we need to recall that the area of a square is equal to the side squared. So let's call the side maybe x, or we'll call it s. Let's call the side s. So the area of the square is just s squared. And if you look at the way this circle is inscribed inside the square, it would take 2 of the radiuses, 2 of the radii, to equal one side of the square. So you could say that the side of the square is equal to 2 times the length of the radius, 2 times the radius. And then I could substitute this expression into that formula for area. So the area of the square in terms of the radius would be 2r quantity squared. Simplifying would lead to 4r squared. And that's the formula for the area of the square in terms of the radius. So if you were given the radius of the circle, plug it into that formula and that would tell you the area of the square. Similarly, we're going to find the perimeter of the square as a function of that radius. So we mentioned before, the perimeter is when you add up all the sides, and this is 4 of the same sides since it's a square. So the perimeter is just 4 times the length of the side, which we discussed earlier. The length of the side is 2 of the radiuses combined. So this is just 4 times 2 times the radius, which is 8r. So the perimeter as a function of r is just equal to 8 times the radius, which if you think about it makes sense, because it would take 2 of the radius to make one side. And there's 4 sides. So you'd have 1, 2, 3, 4, 5, 6, 7, 8 radiuses to get all the way around the square. In example 3, we have the classic open box problem, where you start with the square base, or just any base, or you start with a piece of cardboard, which is just a flat 2-dimensional thing. And then you cut out a square from each corner and turn up the sides. So we're going to actually model that in this video. So imagine that this is a piece of cardboard, and you can see right now it's flat. It's a 2-dimensional piece of paper, or a cardboard, if you will. And it's not a square base, so you'll just have to work with me here. Imagine that it was a square. This, of course, is a rectangle, but imagine the sides were equal to go along with this problem. What I'm going to do is I'm going to cut out a square from each corner. And notice it has an equal amount that I'm cutting out. Each of these lengths here are all equal. So I'm cutting out the same square from each corner. All right, so I'm left with this shape here. Now, of course, my cutting skills leave a little to be desired, so imagine that I have a symmetric shape here. I'm going to form a box by folding up the remaining sides. And voila, there's your box. So what we have is now a three-dimensional object. And this three-dimensional object has a base, and then you take that base and multiply it to the height. And notice how the height is formed. The height is formed by that same length that was used to cut off the square. That's the height you get when you fold up the sides. And so that's how your open box is formed. Also notice that whatever the length of this original side was, let's say I put these two squares back. Whatever the length of that original side was along here, I subtracted 2 of whatever these lengths were. So whatever this length was here, let's call it x, here's another x, I had to subtract 2 x's away from the length to get the length of this side. One of the lengths of the base. So maybe I'll put the box this way. So this would be whatever it used to be minus 2x, and then this length would be whatever it used to be minus x. And then you multiply that by the x, because the x is your height. Let's go ahead and draw what I just demonstrated. We began with, of course, a pretend square. It was really a rectangle, but we began with a square piece of cardboard, and we cut off an equal amount from each corner. And so we'll go ahead and call that x. And according to this problem, the original length of the side was 30 inches. So this started off as being 30 inches. But when you cut off the sides, we were left with this shape here. And so we took off 2 x's from each of the sides. And so this side is now 30 minus 2 of those x's. Then we folded up the sides of the box to create the sides of the paper to create a three-dimensional box. And so this side right there would be the 30 minus 2x. And since this is a square base, this would also be 30 minus 2x because the two original sides were the same. And I subtracted 2x from both sides. And then of course the height you get when you fold the sides up is x, because that was the length, that was the amount we cut off. So when you fold that up, that becomes the height that stands up. So this is the shape we have. And it was an open box because when you fold up the sides, the top is open. Okay, so there's the picture we're dealing with. Now what it wants us to do is express the volume of the box as a function of that length x, this length x here, that we cut off from the corners of the original piece of cardboard. Well, let's just think theoretically what volume is. Volume is the area of the base times the height. The area of the base in this case is the area of a square. So our base begins as a square, and then when you multiply that square by the height, it's like you're stacking that many squares right on top of each other, and it creates a third dimension. So this right here is 2 dimensions. And then you multiply by one more dimension. The height adds a third dimension to it. And then that would give you something with 3 dimensions. So in this scenario, the area of the base is the area of 30 minus 2x times 30 minus 2x. It's the side of the square squared. So it'll be 30 minus 2x, I guess you could say, squared, times the height, which again we talked about was just equal to that very same x. And so this right here would be our volume of that box in terms of this length x that we cut off from each side. Last but not least, in example 4, we have the classic fenced-in yard problem. So Sheila has 1,500 meters of fencing, wants to enclose a rectangular plot. It borders one wall of her house. and she does not put fence along that side that borders her house, write an equation for the area of the yard as a function of one of the sides. So it helps to have like a picture. So let's say, and again, you have to pardon my drawing here. Let's say this is Sheila's house. And she wants to fence in a yard. So let's just say she wants to enclose like this yard here. And so she's going to put up fencing. Okay, that's like a horrible picture, but anyway, you get the idea. Okay, so go like that. So she fences in this yard here, but she doesn't put any fencing along this back wall. So she only puts up 1, 2, 3 fences basically. And she has 1,500 meters of fencing. That's going to come in handy in a little bit. Let's just think about the area of that yard. The area of that yard would just be one dimension times the other dimension. So maybe I'll just call this one X and this one Y. So area of the yard is simply equal to X times Y. Length times width, or base times height, however you want to think about it. The problem is I need to get the area as a function of one of the sides, not both of the sides. So I need to get one of these, either the X or the Y, to be written in terms of the other. So I could just use one variable in here instead of 2. So that's where the whole 1,500 meters of fencing comes in handy, because I know that 2 of these Y's plus 1 of these X's has to sum up to 1,500, because I'm putting up the 1, 2, 3 fences. 2 of them have a length of Y, and then 1 of them have a length of X. So maybe I'll just go ahead and get X in terms of Y. Because it was easiest to solve that way. And then what I can do is I can substitute this expression in for X in my original equation. So in this case, I'll put the area in terms of Y is equal to 1,500 minus 2Y, and then you can multiply that by this Y. And then there is our area in terms of one of the sides. And if you don't like the fact that it was in terms of Y, like if that's uncomfortable for you, you could either just solve this for Y in terms of X, or you can just change the names of these if you wanted. So if you're uncomfortable with that, you could call that one X, you could call that one X, and you could call that one Y. And then you would just switch that to X, and then that to Y. And then you could just switch that to X, if that makes you more comfortable. Okay? So the idea is just to get one of these variables in terms of the other, so that your area is in terms of just one of the sides, not both. So now if I was given this X amount, I could plug it in here and do 1,500 minus 2 times that X, all of that times X, and that would give me the area of this yard.